Hey everybody, so first YouTube video in a while. So we're going to talk a little bit about what we were talking about yesterday, how when a photon hits an atom and hits an electron in that electron absorbs the energy and moves up to a higher energy level. Now if we already have an electron in a higher energy level and it moves down to a lower energy level, it emits a photon. Okay? So our goal is to identify the energy of those photons absorbed and emitted from electron transitions. So on the left here and on the right, well, these are basically the different energies of the electrons in hydrogen and mercury atoms. Okay? Let's just take a second to look at this because we're going to use this a lot today. So hydrogen. At the n equals 1 state, that's down here. All right, at the n equals 1 state, we're going to work with blue today. An electron has an energy of negative 13.6 electron volts. Okay, not joules. Why is it negative? Well, it's negative because it's kind of like the electron's bound to the atom, right? Now, if it's ionized, the energy is 0 because it's no longer bound to that atom. We're going to do some of the math of this in a bit, but just keep that in mind. So a few things I just want to point out here. Look at the energy difference between n equals 1 and n equals 2. That's big, right? That's over 10 electron volts. Look at the energy transition between like 5 and 6. That's really small. So not all energy transfers are equal. That's why it's important to do this stuff mathematically. All right. Now, this is mercury. More or less the same idea, but for whatever reason, the energy levels they use for mercury are letters and not numbers, where A is the ground state. Instead of n equals 1 being the ground state, A is the ground state. I don't know why they do it that way. That's just how they do it. Okay? But again, similar ideas, like not all these electron transitions are the same. Like obviously the biggest one, again, is between the ground state A and the next state up B. But it's not really that predictable aside from that. Like there's this E one here. Okay, there's a transition that's bigger than this one here. Now I think maybe the reason for that is that they don't list them all here because it says a few energy levels for the mercury atom. So maybe there are a bunch in there that they don't fill in. That's why they use letters and not numbers. I'm not really sure. But anyway, that's what we're working with here. All right. So let's work through this. We're going to work with this chart a lot today. This is on your reference table, by the way. So how much energy does an electron in the ground state of a hydrogen atom have? Well, if we look, hydrogen, ground state's at the bottom there, negative 13.6 electron volts. All right. Now convert that to joules. All right, so 1 electron volt was equal to 1.6 times 10 to the negative 19 joules. That's on your reference table. Where exactly? If we go to the reference table, we have, I'm looking for it, it's right here, 1 electron volt, 1.6 times 10 to the negative 19 joules, all right? So we have negative 13.6 electron volts times 1.6 times 10 to the negative 19 joules over 1 electron volt. How do I know to put joules on top? It's always what I want over what I have, right? If I throw this in my calculator, which is right next to me, let's see, I get 13.6 times 1.6 times 10 to the negative 19. I get negative 2.18 times 10 to the negative 18 joules. Now, it's important to convert this to joules. We'll see in a little bit, or why it's so important, all right? How much energy does an electron in the E level of a mercury atom have? Well, E, if we look there, negative 1.3 times 10, or excuse me, negative 3, I don't know what I was just saying, negative 3.71 electron volts. All right, so again, we're going to convert that the same way. Negative 3.1 electron volts times 1.6 times 10 to the negative 19 joules over 1 electron volt. Electron volts cancel. And let's see what we get here. It looks like 4.96 times 10 to the negative 19 this time. All right, so try that out in your calculator. These numbers are big, and we're using some other big numbers or small numbers today. You got to practice doing them in your calculator so you don't make any calculator mistakes. All right, so an electron in an excited mercury atom is in energy level G. what is the minimum energy required for a photon to ionize the atom? All right, so let's try this out. Well, let's try out a few things first. Um, First off, energy level G is, it looks like negative 2.48 electron volts, right? So that's going to be our initial energy, 2.48 electron volts. Now our final energy, if we ionize it, is 0. Just to show you, this equation is on our reference table, right? If we go through, there's a modern physics section. Energy of the photon is equal to the initial energy minus the final energy. All right. So what is the minimum energy required for ionization? Now, one thing that is commonly recommended here is that you ignore the negatives in the energies. Usually they ask for like the magnitude of the energy or whatever. I tend to ignore the energies. I don't make any of them negative. It works out for me. So I'd recommend you try the same. So energy of the photon equals 2.48 electron volts minus 0 electron volts. So energy of the photon is 2.48 electron volts. Converting that to joules. That's a J over there. Let's see, that comes out to be 3.973. That's, can't write. 3.97 times 10 to the negative 19 joules. All right, and that goes over there. Now, a red photon in the bright line spectrum of hydrogen gas has an energy of 3.02 times 10 to the negative 19 joules. What energy level transition does an electron in the hydrogen atom undergo to produce this photon? So one thing I just want to show you is that there's no joules up here. So we have to convert it to electron volts. That's the first thing we need to do. Now we want electron volts. So we put it on top. The 1.6 goes on the bottom now. And we get 1.89. Now this 1.89 electron volts is a transition in a hydrogen atom. So we need to find which two are 1.89 electron volts apart. All right. So it's not these two, right? That's way too big. But let's try the next one. Let's look at this transition here. So we have 3.4 and 5.1. Or 1.51, excuse me. So that one seems like it's about right. Okay. 3.4 minus 1.5 is 1.9. So that's n equals 3 down to n equals 2. Okay. Now is it absorbed or emitted? So we're producing the photon, right? So we're losing energy. So that's from n equals 3 to n equals 2. Because at n equals 3, we had negative 1.5. N equals 2, we had negative 3.4. By the way, when I said that whole thing about ignoring the negative before, it can get confusing. Really, what you have to emphasize, like really look at, is just the difference in the two numbers. The difference in these two numbers is 1.9 electron volts. Okay, called delta energy, change in energy. You know, photon, or you just call energy photon. Don't get hung up with, wait, is it negative 1.5 minus negative 3.4? Is it negative 3.4 minus negative 1.5? Do I make them positive? Just look at the difference. That'll make your life so much easier. Okay? So that's the transition it corresponds to. All right. So this one here, I want you to read on your own, try on your own, pause the video and see how you could do. It's actually a claim evidence reason. We haven't done these in a while, but just remember with claim evidence reason stuff that you know how to do them. It's just kind of knowing what to put in claim, what to put in evidence, what to put in reason. So give it a shot, take a minute, pause the video, and check it out in a minute. All right. So if we look here, it says photon X is released from a hydrogen atom when an electron moves from n equals 4 to n equals 2. Photon Y is released from a hydrogen atom when an electron moves from n equals 2 to the ground state, so n equals 2 to n equals 1. Your classmate claims that photon X has more energy than photon Y because it moved 2 energy levels as opposed to 1. I kind of forgot to put the next part in, but basically refute or deny, or support or, support or refute, or maybe agree or disagree. I know the answer already. I'm going to say that I'm going to make a claim saying that I'm going to be right. I'm going to say photon Y has more energy. That's my claim. Now, well, let's kind of build our evidence. Well, I know that if I go from n equals 4 to n equals 2, let's look at those energy levels. N equals 4 is 0.85, and n equals 2 is 3.4. So we have 0.85 and 3.4. So the amount of energy that photon will have is the difference between those two. Again, don't really focus on positive or negative. If you wrote them both down as negative, just subtract them, and it's really just the difference. That's 2.55 electron volts. By the way, this was photon X. All right, now let's look at photon Y. That's n equals 2 to n equals 1, the ground state. So n equals 2, we just said, is 3.4 electron volts. Let's look at n equals 1. That's 13.6. So that comes out to be 10.2 electron volts. All right, so there's our evidence. So let's go to our reason. We have to kind of basically talk about our claim, and did we support it or not with our evidence. So our reason is photon Y has more energy. Because n equals 2 to n equals 1 has more energy than n equals 4 to n equals 2. All right, so we just showed it there. So just because one of the photons moved 2 energy levels does not mean, or one of the electrons moved 2 energy levels, doesn't necessarily mean that it had more energy. Now, if they were both ending up on n equals 1, you would find of the math that the one that moved 2 or moved more would emit more energy. But it's kind of important for you to do the math, okay? That does help you a lot. Now, one important thing I want to mention here, and I mentioned at the end of last class, these photons that we're talking about, it is the only photon that is emitted. For example, I should be clear with what I just said there. Photon X is released from a hydrogen atom when an electron moves from n equals 4 to n equals 2. So anytime any hydrogen atom in the universe lets an electron move from the n equals 4 state to the n equals 2 state, it releases a photon with exactly this much energy, period. No more, no less. Same here. From n equals 2 to the ground state, it releases a photon with exactly this much energy. No more, no less. Absorption works pretty much the same way. It's slightly more complicated, but basically works the same way. An absorption we spoke about was this one here, number 3. An electron is ionized. When something's ionized, it can actually be a photon that's a little bit stronger, because all that extra energy, where can it go? Normally when it goes from like the n equals 2 state up to the n equals 1, or the n equals 1 state up to the n equals 3 state, that's a very specific energy transfer, okay? So you need a very specific photon. But when you get ionized, the electron leaves. So that electron that leaves can take the extra energy. So you can actually have a much stronger photon hit the electron, be absorbed by the atom, and release the electron with energy. Okay, so there's a little bit more leeway when you're ionizing an atom, because there's an extra place for the energy to go. So just looking at these pictures, on our ways down, okay, we go from here to here, higher state to lower state, we are going to release photon. We go from a lower state to a higher state, we're going to absorb a photon. Let's just do a few more examples of stuff like this. We do have to talk about something else, though. The energy of a photon can be determined by this equation here. Energy of a photon equals h times frequency, or h times c divided by wavelength. What do all these things mean? Well, easy energy of the photon. This right here, h is Planck's constant. That's right below. Okay, we'll talk about that in a second. F is frequency. All right, h is Planck's constant again. C is the speed of light. Three times 10 to the 8th meters per second. And h is wavelength. Wavelength is measured in meters. Frequency is measured in hertz, which is also 1 over seconds. Now, this is Planck's constant. It's on your equation sheet on the first page. Also, these equations are right here. On the first page, we have Planck's constant. Where is it? H, Planck's constant, 6.63 times 10 to the negative 34 joules times seconds. All right. So first question is, how does frequency of a photon relate to its energy? Well, look at this equation here. Energy equals h times f. If f goes up, energy goes up. Okay, so if frequency goes up, energy goes up. If frequency goes down, energy goes down. How does frequency of the photon relate to its energy? Oh, I wrote the same thing twice. I meant to write wavelength. All right, well, how does it relate to energy? Well, if we look here, we have energy of the photon equals hc over lambda. Well, if the wavelength goes up, it's in the denominator. That's going to make the energy go down, and vice versa. If this goes down, if the denominator gets smaller, the energy gets bigger. All right, but it's just a plug and chug equation. We'll see how to use it right now. All right, so the Great Nebula in the constellation Orion consists primarily of excited hydrogen gas. The electrons in the atoms of excited hydrogen gas have been raised to a higher energy level, or to higher energy levels. When these atoms release energy, a frequent electron transition is from the n equals 3 to the n equals 2 energy levels, which gives the nebula one of its characteristic colors. Okay, that wasn't a question. So determine the energy of an emitted photon when the electron transitions from n equals 3 to n equals 2. So let's see, n equals 3, so that's our energy initial, n equals 2, that's our energy final. Got to go to the top, right? So n equals 3 is 1.5, n equals 2 is 3.4, 1.51 electron volts, 3.4 electron volts. All right, so our energy of the photon is the difference between those two. 1 point, I forgot what that was already. 1.89 electron volts. By the way, before it was 1.89 or 1.9. It's not a big deal though. But 1.89 electron volts. We are going to have to convert that to joules though, so let's do that. 1.89 electron volts times 1.6 times 10 to the negative 19 joules over 1 electron volt. We get 1.89 times 1.6 times 10 to the negative 19. I get 3.02 times 10 to the negative 19 joules. All right. Calculate the frequency. Well, we have the energy in joules. That's important. So let's start with that. E equals HF. So we know our energy, 3.02 times 10 to the negative 19 joules. I'm going to leave the units in for now just so we can see them. Planck's constant, 6.63 times 10 to the negative 34 joules times seconds. Looking for the frequency F. Notice how joules here cancels with joules there. Okay, and since frequency has units of 1 over seconds, those are going to work out nicely too. So we have 3.02 times 10 to the negative 19 divided by, be careful here, use parentheses, 6.63 times 10 to the negative 34. And I get a very high frequency. Let me just double check something. Oh, I made a small mistake. Give me 1 sec. E negative 19 divided by 6.63 negative 34. There we go, that's a little better. I'm getting a frequency equal to 4.56 times 10 to the 14. All right, that's my frequency. What color is that? So this is actually how we discover like what makes up certain, I guess, gases or objects in outer space, is we look at the colors and we can determine like, oh, you know, hydrogen has these very characteristic frequencies. It gives off this frequency very commonly. Mercury, we could have done the same thing with Mercury. We could have figured out, oh, like this type of Mercury exists in this nebula. So let's look at what color this is. So 4.56 times 10 to the 14 falls in the bin of red. So that'd be red light. All right, so there we have it. We're going to work more with this. We just did some math today. Maybe we'll do some application stuff of it next class, all right? Have a good one. Fill out the Google form.